So welcome back. Now I take a time, it's a short one. It's a relatively short lecture, but I'll talk about performance. In fact, we have already talked about performance with data frames because data frames are already one way of increasing performance because you have less bits in the memory. You have less to read from disk. You can throw away the data you don't need very early. And on top of that, you have a high-level language, namely Spark SQL, that allows you to highly optimize and rewrite the query plan if the query was not efficient. But in fact, there are plenty of other things you can optimize. And since you are computer scientists, it's actually things that you will probably need throughout your career to understand. There are many ways you can interact with these systems. But at least today, you might not just use Spark SQL, but you might also have to use a host language to interact with these systems. Maybe Python, maybe Java, maybe Scala, maybe C++, maybe other languages. And so in order to do this, you need to be aware of the underlying system in order to make things smooth. Again, I told you yesterday, maybe in the 22nd century, we'll have so many optimizations that this is no longer needed. But today, it's still important to have a bit of awareness of what's going on, because there's a lot of things that you can do. It might, for some of you, come as a surprise that I will tell you things that might contradict what you heard in object-oriented programming lectures. Who had object-oriented programming as lectures? Many of you, right? So do not be scared. I will contradict a few things that you heard in them. It doesn't mean that I disagree. It just means that it depends on the scope of application of what you are doing, right? All the advice that you got in these object-oriented lectures, they apply for small applications on a system. It's important to design it well with encapsulation, with subclasses, and with a clear API designed by contract, and so on and so on. So all these design, it's actually very important to get very good software engineering. However, this is a bit in conflict with large-scale performance. When you actually want to make a system very fast at large scales, you have to compromise on these things a little bit. So I'm going to try to give you an intuition. Who already worked with a company like Google, or yes, some of you, right? Yes. So you've probably seen in the style guide, because every company gives you a guide on what to use and what not to use in a language. Many companies forbid a few things. For example, in Java, some companies do not allow using subclasses. They only allow you to use interfaces, right? And this is the sort of things that actually helps with performance. So first, we've done a lot already, right? We even started a bit on querying. So when you want to have performance, a lot of that is going to happen in your brain. You need to think about what's going on. And there are a few fundamental rules of thumb of how to think about these things. So imagine you're running a query and the system is slow, and you don't know why, and you would like to improve the system. What's happening is that if it's slow, then it means something is slowing it down. That something is called the bottleneck. And there is somewhere something that is eating up all that time, preventing the system from being fast. So bottleneck looks like this. It means that some part of your system might not be fully used, but there is a part of the system that's completely overloaded, right? That is actually preventing the performance. Now, very roughly speaking, and on a high level, there are really only 4 ways you can have a bottleneck, fundamentally. Maybe there are others, or there will be others, but these are the top 4 that you need to think about. The first bottleneck you might have might be the memory. You don't have enough memory. The memory is completely full. It's spilling to disks like crazy. And of course, that is slowing you down. That is the first thing that can happen. A second thing that can happen is that it's the CPU that is overloaded. Maybe you have so much parsing to do, or maybe your data is encrypted and you need to decrypt it, and that takes a lot of CPU time. So that might be the CPU. Or it might be the disk I/O. It might be that you have so many bytes to read from your disk that you spend all of your time reading, and this is what is slowing you down. That bottleneck, we already know how to solve. We go to MapReduce and Spark, right? If you have the disk I/O bottleneck on your machine, we've seen that the hard drives have evolved so much that we cannot read the data fast enough anymore. So the disk I/O is the bottleneck for which MapReduce and Spark are actually helping. And finally, you have the network I/O. Maybe the intermediate data that you have in MapReduce and Spark, there's so much of it that the time it takes to flow over the network and go across machines is slowing down the system because you know that the network bandwidth is limited, the number of bytes you can send per second. In fact, there are even computer network researchers that are trying to optimize that at the network level, how to optimally transmit the packets. But the good news is that from an abstract perspective, I'm not a hardware researcher, right? But from an abstract perspective, it's one of the four. So the first step, if your system is slow, your first step is to figure out which one of these four it is. It cannot be several. It has to be exactly one. That is one of these. It's not going to be two or three. For example, the source might be the memory, and you can see it because the CPU is not used 100%, the bandwidth of the disk is less, and so on. But you can see in the system activity, you can see that the memory is completely full. Or, no, in that case, the example is the CPU, not the memory, sorry. So in that case, the memory is not full and the CPU is overloaded. And you see that your CPU is running, all your CPUs on the cluster are running 100%. We use the terminology CPU bound. CPU bound means that the bottleneck is the CPU. It could also be disk I/O bound in the sense that what's slowing you down is the disk I/O. It could be memory bound, your memory is completely full. Or it could be network I/O bound, meaning that it's the shuffling that is causing the problem. Or maybe you're reading too much data remotely and not from short-circuiting HDFS, right? So it's one of the four. And the first thing to do is to figure out which one of the four it is, right? Once you figured it out, it might be tempting to say, well, that's easy, right? If I have a memory-bound query, I just buy more memory, right? I just need to switch to other machines that have more memory, right? Or I need more cores, or I need to parallelize more with more machines, or maybe I need to use a bandwidth in the network that is larger, right? So it's tempting to do that, but really resist that temptation. Throwing more money at the problem is not the way, right? You need to really optimize what code you wrote, because there's very often ways that allow you to improve it. So first, you should really have this automatic thought. If your problem is the disk I/O, you cannot read fast enough from the disk, then the solution is a system like MapReduce or Spark, or to add more machines in order to spread the disk I/O. It's not the only one. In fact, there is another way, which is, for example, using Parquet instead of JSON, because then you have less bytes to read from the disk. And on top of that, you don't even need to read all of them if you can project away and exclude some columns, right? Is there a question on Zoom?
Yes, the question is about what kind of tool can we use to check if the program is, for example, disk I/O bound. I can imagine how to do this on single machine, but how this could be done on distributed system.
So this is a bit vendor dependent, and this is for example, when you are connected to a cluster on Amazon, let's say, you can SSH yourself to the machines, right? So you can SSH yourself to the machine. You can look in real time what's going on the machine. Another way is to connect to the Spark history server. If you're using Spark, the Spark history server has a lot of useful information. It shows you all of the query plan, all of the stages, all of the jobs, the number of tasks that you have. It even tells you if data gets spilled to disk and so on, right? It tells you that. So this is also a very valuable tool. Another tool is the logs of the machines, right? And yet another tool is vendor dependent, right? Amazon has monitoring tools. You can see in the console when you have machines blocked there, it shows you in real time the CPU usage, the memory usage, even aggregated on the entire cluster. So you have plenty of tools at your disposal. And doing that is really something that you get practical hands-on experience with, right? But you really have to use all of these in order to figure out. It's really like a Sherlock Holmes investigation, right? You need to see. Does it make sense? These are just a few examples of tools that you can use. There are also profilers, right? If you use Java, for example, you can download a profiler and it even tells you in what methods time is spent. So there's plenty of tools that you can use. What I'm telling you today is really on a high level what you can do. All right. So in terms of, you need to understand for this the ballparks of what to expect in terms of on hardware. So you might remember the latency and so on that I told you. There's these prefixes that you already know that are in the positive powers of 10. It turns out that you also have them as negative powers of 10, right? So these you might know: milli, micro, nano, I guess all of you, pico, femto, maybe less, and atto, zepto, yocto, even less, right? So it's a good idea to know them. In terms of hardware, I think we use maybe the first three, but we are not yet at the smaller ones, right? Maybe the first four, because pico might, you don't know, it might happen soon, right? Atto, in terms of time, is now what you achieve in physics, the attosecond. In fact, people won a Nobel Prize for that this year on the atto scale. Okay. So I put here typical latency, and I did a very bad job of actually contrasting the thing, but you can look at them offline. I'm not going to comment on these. I just put them here for reference. It's a good idea to have a ballpark of these, not the exact values, right? But to know, like, is it nanoseconds, is it milliseconds, and so on, right? So you just need to kind of have this intuition that when you are in the CPU, it's typically nanoseconds, right? When you are dealing with the memory and the network, it's typically going to be microseconds. And when you are dealing with disks or the internet, but far away over the globe, then it's going to be milliseconds, right? So just for this intuition. It might change. Maybe in 20 years, we have made so much progress that it changes, but this is the idea, right? Nanoseconds when it's the CPU, microseconds when it's the memory or the local network, and milliseconds when it's the disk or over the Atlantic Ocean, right? Just as a very coarse ballpark. In terms of transmission, it's also good to know roughly what we are dealing with here. In terms of networks, when you know that internet typically now give you gigabits, right? Gigabits per second, right? Die schnellste Schweiz der Welt. I loved that motto. So this is the ballpark, so gigabits, but in fact, in a cluster, you can achieve tens or hundreds of gigabits per second. What about the disk input-output? The ballpark here is in hundreds of megabytes per second. A few hundred megabytes per second is what you can squeeze out of a single disk, right? And in fact, when you have these values right here, it's very easy to just take a piece of paper and a pen and compute a little thing, right? For example, you can take the whole size of the data set. If you want to know if it's IO bound, that's another tool you can use, a pen and a paper. Imagine that you have a data set, and that data set is, let's say, 10 gigabytes. You have 10 gigabytes of data, and you're trying to read, let's say it's JSON, and you're trying to read these 10 gigabytes of data locally with your machine. How do you know if the problem is the disk? When you can quickly calculate, right? Imagine that just the time it takes to read it. So let's say 200 megabytes per second as a rough approximation. So I can read 200 megabytes per second from the disk. It means in 5 seconds, I can read a gigabyte, 5 seconds. And to read 10 gigabytes, I need 20 seconds, right? So now you run your query and see how much time it takes. If it takes 20 seconds, then you know you're limited by the disk and you know it's gonna get any better, right? It's not going to get any better than that because you're already reading the maximum number of bytes per second. But if your query takes 5 minutes and your calculation is that just reading it should take 20 seconds, then you know the problem is not the disk. It's probably something else, maybe the memory, maybe the CPU. So it's always a good idea to do that because that drives your decision. If it's actually the 20 seconds and the disk IO is the problem, then just book a cluster and go with Spark or MapReduce. If, on the contrary, it took you 5 minutes, save yourself a bit of money, don't get to a cluster, and try instead to optimize your code with the CPU or the memory consumption, right? So this is the sort of things you can do. So all it takes typically is a division, a pen and a paper, maybe a calculator. You can use actually at the exam the calculator in Python in the notebook, but it can really help, right? For whom is that intuitive? Right? Okay, so sometimes simple math can already be extremely useful. All right, now, in terms of response times, probably have just a few minutes, but I'll tell you quickly. When you want to measure a performance improvement, how do you quantify by how much you have improved your system? You need to look at the total response time, meaning that it's not only the latency, it's just the latency plus the transfer time, meaning the data flowing around. That's the total response time. It's the moment between clicking the button in the Jupyter notebook and the results appearing in your notebook, end to end. And typically, you compute the speed up by dividing the total response time. Some people call this latency, actually. This is why I use it here. So some people call latency the total time. So divide what it used to take, divided by what it takes now. If, for example, if you have 3 seconds before you improve and now you improve and it's 2 seconds, you get an improvement of 1.5. So you improve by 50%, right? So this is how you measure and quantify an improvement, right? Now there is a law, which is Amdahl's law, that computes the speed up based on 2 parameters. The first parameter, P, is the part of your system that is parallelizable, and then you try to parallelize it. Let's say 30% of what you have is parallelizable. And on the part that is parallelizable, you have a speed up of 2. You manage to make it twice as efficient. Then that formula right here gives you the overall speed up. And now you see, because not everything was parallelizable, if all was parallelizable, you would have a speed up of 2. But since we only can improve the part that is parallelizable, my overall speed up is 18%, right, as opposed to 100%. So this is something you need to be aware of. Parallelizing helps, but it only helps on the part that is actually parallelizable, not on the rest, right? For whom does it make sense? All right, so this is your law, and I'm going to give you another law next week called the Gustafson's law, and we'll discuss them. Just before you go, just let me know how much of what we did you understand. Of course, if it actually lets me ask you this. Where are we? We are right here. So let me know, and then you are good to go. Well, what did it look like? Yes, very good. About 80%. Okay, awesome. Okay, so thank you very much for attending today's lecture. Enjoy the exercise sessions, enjoy the graded quiz, and I'll see you next week on Tuesday for the continuation of the lecture, and then we'll start with document stores and MongoDB probably next week. Thank you very much. Goodbye.